So we know if we are going to integrate a rational function, we need to find a partial fractions decomposition. And to do that, we start out by factoring the denominator of the rational function. And when you factor a polynomial using real numbers, there are a couple different possibilities. So some of your factors will turn out to be linear factors, that is degree 1 factors. But using the real numbers, it's also possible to get unfactorable degree 2 factors, for example, x squared plus 1. So let's have a look at an example like that so we can see how this affects our partial fractions decomposition. So since we have a linear factor, x plus 1, you would expect that we get a term in our decomposition that has x plus 1 in its denominator, and that's true. And then there's some unknown constant in the numerator. But what about the unfactorable quadratic term? Well, you might expect that there is a term in our decomposition that has x squared plus 1 in the denominator, and you'd be right. But the difference here is that because this is an irreducible quadratic, it turns out we need not a degree 0 in the numerator, but a degree 1 polynomial. And a degree 1 polynomial will have an x term and a constant term. So we might have some constant times x plus some other constant. So you can see that the numerator you get in a partial fractions decomposition from an irreducible quadratic is more complicated than for a linear. So irreducible quadratics in a partial fractions decomposition are kind of annoying because you just get more constants from them. Okay, so now that we have this partial fractions decomposition written down, we can use our same tricks to find the constants. Clear denominators, so multiply both sides of this equation by x plus 1 times x squared plus 1. We get x squared equals a times x squared plus 1 plus bx plus c times x plus 1. Okay, and now we can play the same game of plugging in x values. And we should start by using all of the nice x values, but there's only one nice x value. Right? This x squared plus 1 term, it doesn't have any nice x values because it doesn't have any roots. But this x plus 1 term, it has a root at x equals minus 1, so let's use that. So x squared is 1 equals a times x squared plus 1 is 2 plus, now this gives us minus b plus c, right? Don't forget to plug in our x value right there, times x plus 1, but that's 0 for this x value. So we get, looks like a is a half. All right. Now we're out of nice x values, so already we have to just start plugging in random x values. Don't make them random. I mean, choose x values where the arithmetic is easy. 0 is a nice one, so that gives us 0 equals, right, we already know a is a half, so let's use that. 1/2 times 0 plus 1, so 1, plus b times x, but x is 0, so 0 plus c times x plus 1, so that's 1. So it looks like c is minus 1/2. And then finally, choose maybe x equals 1. So this gives us 1 squared, but that's 1, equals a, which is a half, times x squared plus 1, which is 2, plus b times 1, so b, plus c. We already know c is a half, or minus a half, so b minus a half, times 1 plus 1, so 2. So this gives us, let's see, 1 equals 1 plus 2b minus 1. So we get b is a half. Okay, so now our partial fractions, I'm kind of out of room, so I'm going to write the partial fractions decomposition up here. It's a, which is a half, over x plus 1, plus bx plus c, so b, which is a half, x plus c, so minus a half, over x squared plus 1. All right, and then how would we integrate this thing? Remember, for us, the goal of finding partial fractions decomposition is this is how we're going to integrate rational functions. So this first term, when we integrate this, it's just going to give us some sort of natural log. That's no problem. For the second term, there are actually two pieces. There's the part with the x in the numerator, and then there's the part with the constant in the numerator. If you look at think about integrating the part with the x in the numerator, it looks like a u substitution is going to do the job for integrating that piece. But then with the part with just a constant in the numerator, well, that's going to give us some sort of inverse tangent, possibly after we do a substitution, but not in this case. So again, each term that comes out of this partial fractions decomposition is something that we can integrate. Let's look at one more example. So 1 over x minus 3 times x squared plus x plus 1 squared. So the new thing about this example is the fact that we have an irreducible quadratic that's squared. So what will the partial fractions decomposition look like? Well, there's going to be a term with x minus 3, so some constant over x minus 3. And then, of course, there's going to be a term, so this quadratic, x squared plus x plus 1, this is irreducible. Maybe we should have noticed that at the very beginning. If it did factor, we would just factor it. But it doesn't factor, not even using irrational numbers. So it's irreducible, so we get a term with x squared plus x plus 1 in the denominator. And the numerator is some first-degree polynomial, so bx plus c plus, okay, but since it's squared, we need a term that has x squared plus x plus 1 squared in it. And again, a degree 1 numerator, so dx plus e, I guess. Okay. So 5 constants. This is going to be unpleasant. But in principle, it works exactly the same way. Start out by clearing your denominators. So multiply both sides by x minus 3 times x squared plus x plus 1 squared. On the left-hand side, we get 1. On the right-hand side, we get a times x squared plus x plus 1 squared plus bx plus c times x minus 3 times x squared plus x plus 1 plus, and then our final term, dx plus e times x minus 3. And then again, we can just plug in some x values. In fact, since we have 5 unknowns, a, b, c, d, and e, we're going to have to plug in 5 different x values. And among those, we should include x equals 3, because that's the nice one. But we're going to have to choose 4 other x values. And what we'll end up with is a system of equations where a, b, c, d, and e are the unknowns. And we'll solve that linear system of equations for a, b, c, d, and e. I won't do that because I don't want to solve a 4x4 system right now, but that's the general idea. For partial fractions, all you need to do is plug in enough x values to get a big linear system for all of your unknown coefficients, and then solve that linear system. There are actually a few other tricks, a few variations for how to find a, b, c, d, and e. One nice one is if we multiply out everything on the right-hand side and everything on the left-hand side, then we get a polynomial on the left-hand side and another polynomial on the right-hand side, but those are supposed to be the same polynomial, so we could just set coefficients equal. Let's do an example like that just to see how it works. So let's do, how about 4x plus 2 over x minus 3 times x plus 1. Okay, so we know that our partial fractions decomposition is going to look like a over x minus 3 plus b over x plus 1. And then clear denominators, we get 4x plus 2 equals a times x plus 1 plus b times x minus 3. Now for this particular example, plugging in the nice x values is the easiest way to go, but I'm just trying to demonstrate this idea of multiplying out the polynomials. So we can multiply out and combine like terms on the right-hand side. So we have ax plus bx, so that's a plus b times x. And then for our constants, we have a times 1 minus 3 times b, so a minus 3b. Now both sides of these equations are polynomials, and they're supposed to be the same polynomial. But when you have everything multiplied out and like terms combined like this, the only way for these two polynomials to be the same is if the coefficient on x is equal to the coefficient on x on the right, and so that means 4 equals a plus b. And also the constant term on the left has to be equal to the constant term on the right. And that means that 2 has to be equal to a minus 3b. And you can see what this gives us is a 2-by-2 system of linear equations that we can solve for a and b. I think for this, maybe it would be easiest to subtract the second equation from the first. We get 2 equals, the a's cancel, and we get 4b. So b is a half. And now we can put that back into the original, or into the first equation up here. We get 4 equals a plus a half, and so a is 3 1/2, or 7/2. So now we know a and b, so we could write down our partial fractions decomposition. This trick of multiplying everything out and then setting coefficients equal is a pretty slick trick, but it still just gives you a system of linear equations, so it doesn't get you out of having to solve this linear system.